Okay, well, our next speaker is João Silva from Newcastle also, and he'll be speaking about elementary groups.
Okay, thank you for the presentation. So today I will be talking about my PhD project with George Willis and also Stefan and Colin at the University of Newcastle. So let's begin. Just to give an outline of what we will be talking about today. First, I will give an introduction to the general things that will be necessary to understand my talk. I already saw that Colin already talked a little bit of elementary groups, so that part will be easier, but yeah, I will still be talking about those. And then I will talk about what we are focusing more at the moment. Like there are more things related to our project, but this is the main thing on the next few months. So I will be talking about it. And let's begin with the introduction then. So as many of you know, group theory has many applications. And when you look at group theory, for the finite group theory case, it's well developed. You have the classification of simple groups. You have many things. So natural step would be going through the infinite case. And what happens when you jump to the infinite case is that you can have more than one house of topology. You can have the discrete one, but many times you can have others. And these topologies many times are also related to the structure of the sets you are acting on and such things. So understanding the group as a topological group, not just as an algebraic group, is useful for us to understand the group structure itself and also the space that we are studying. So it's kind of interesting to look at groups not just as groups, but as topological groups. And for an argument, why would we study totally disconnected locally compact, which I will shorten for TDLC, is that if you have a locally compact group, so here we have, for instance, G. So given G, you will always have the connected component, which is closed and normal subgroup. And you will have that the quotient under the connected component of the identity will be always be a totally disconnected locally compact group. So in some way, what we are saying is that in the general locally compact case, to understand it, you need to understand a lot of the connected case, which would be this side, and the totally disconnected case. So in our research, we are focusing most on the totally disconnected side of things. And now, just another tool that will be useful for us will be ordinal numbers. So ordinal numbers are important to mathematics because when you can index things with ordinals, you get a new tool for proofs, which would be induction. So it's quite useful to have ranks or things like that related to ordinal numbers to get these tools with us. And so how do we define it? One idea that one can think about is when you ask, for example, some kids to try to compete and say what is the biggest number they can think of. At some point, they might, at the beginning, they might start with normal numbers. And then at some point, they might begin saying things like infinity plus 1, infinity plus 2, infinity times 2, and so on, so on. And in some sense, ordinal numbers are a way to formalize this raw idea. So I will say that an ordinal number will be a set containing all the things smaller than it. So the 0 will be the empty set. The 1 will be the set that contains the 0. So it will be just as represented here, it will be just 1 bar. The 2 will be the set that contains 0 and 1. So it will be these 2 bars. And if you have omega, which is the first countable ordinal, and it's also known as the natural numbers, you have all the natural numbers inside it with the usual order. And then you can get all the other ordinals. So for example, omega plus 1, you are just saying that omega is greater than every natural number. So you get 1 extra bar that's in front of all of them. Omega plus 2, you get a bar that is bigger than omega, and so on. So you can have omega 2 also, which would be 2 copies of omega, one after the other. And yeah. So how does ordinal numbers connect to, so first, let's talk about the main structure that we are studying, elementary groups. The idea that we have here is profinite groups and discrete groups are groups that arise a lot naturally when you are studying totally disconnected locally compact groups. And you are just making all the groups possible with some steps. And that's how you kind of define elementary groups. So the class of elementary groups will be the smallest class. We call it cursive V of totally disconnected locally compact second countable groups, such that it will contain all second countable profinite groups and countable discrete groups. You will have that if a group is such that a normal subgroup of it is inside this class and the quotient of it is inside this class, then the group itself is inside this class. And if a group is such that it's a countable union of open subgroups of each, such that each open subgroup is inside this class, then the group itself will also be inside this class. So here you begin with profinite and discrete groups, and you have two operations to make everything else step by step. And this idea of creating things step by step is what makes the first definition of rank make sense. Like we have a rank for these groups, and the first idea that Philip Wesolek had was just to look how many steps you take to get to the groups that you define, and with this you can index your groups with countable ordinals. And with this, like I said, you have all the tools that you want, like induction and so on. That is also another rank that we are mostly using at the moment, because it has some more desirable properties, but I won't go much into depth with it. So given the structure of elementary groups, we can associate it with some rank, which will also always be a countable ordinal, such that for each elementary group, you can give a unique countable ordinal for it. And some open question related to the rank, which is one of the main things that we want to work with, is if we can find a countable upper bound for the elementary rank, or if there is no countable upper bound. And two other equivalent ways to write it is, does that countable ordinal has an elementary group with it as a rank? Or is that a group that achieves maximal countable rank? Or can you always get a group with bigger countable rank? So with this, we have a general introduction to the main ideas of our work. And now to talk about what we are working at the moment, the profinite matrices. First, I will give the general idea of what we want to do with it. So here, what we are doing are creating profinite groups that can be profinite rings, in this case, that can be indexed by ordinal numbers. And what we wish to do with this is make these profinite groups subgroups of elementary groups in such a way that we can also increase the rank with the ordinals too. So because we are indexing by ordinals, maybe we can, it would be easier to do it step by step in a way that there will still be, how do you say? There will still be increasing the rank. And to define it, I will need to talk about Cantor normal form, which is, you can give for the ordinal numbers the usual order, which will be a well order, which is given just by seeing if an ordinal is bigger than the other. But there is also the Cantor normal order, which you are just looking at the ordinals as polynomials over omega. And you define this order kind of like coordinate-wise. So for example, we get here the ordinal omega 2 plus 2. So because you can decrease 1 in the omega coordinate, this ordinal is bigger than omega plus 2. And if you decrease 1 in the omega coordinate again, you can see that it's greater than 2. But for instance, if we get omega squared plus 1, this ordinal in the usual order would be greater than omega plus 1. But because there is no omega coordinate here, you cannot compare them. So this order, even though in the usual order they would be one greater than the other, in the Cantor normal form they are not greater than the others. And what is the desirable property that we have when we are looking at the Cantor normal form? It is that when you look at one ordinal, there will be only countable many things that will be less than that ordinal. So with the, this is the desirable property that we want to use when we are defining our triangular matrices rings. So now, here I'm showing an example. I define the group as tri gamma p. So gamma will be an ordinal and p will be the profinite ring that you are using. And here I will just give an example to show how we define it. The idea is, given the ordinal, you want to index your columns and rows with this ordinal. So omega 2, you get all the elements inside the omega 2, which is 0, 1, 2, all the natural numbers, omega, omega plus 1, omega plus 2, omega plus n for all natural numbers. And then you do the same for the rows, omega, omega plus 1, omega plus 2. And what you want to do is, given the column, for example, here we have the column omega plus 1, right? So you have the coordinates in this column that will be non-zero are only the coordinates such that the row is less or equal than the column. So omega plus 1 is less than omega plus 1. So this point here can be non-zero. Omega is less than omega plus 1. So this can be non-zero. But for example, here, omega plus 2 is greater than omega plus 1. So this will have to be 0. And the same here, 2, you cannot compare 2 with omega plus 1. So this one also has to be 0. And because we have this, like I said before, the Cantor normal form is the Cantor normal order is such that you can only have finitely many elements less than your ordinal. So with this, you can define well multiplication in the usual way and addition in the usual way, and you will have a proper ring structure to it. And now for some results that we were already able to prove is that given a profinite ring and gamma ordinal, you can give this ring a profinite ring structure. And the idea of it is that given an ordinal, what you want to do is, for example, I get this coordinate here, right? I can just I will get the group that this part, and this part are 0. This part are the only, are all the parts that you have one of both coordinates less than omega plus 1, like the coordinates alpha and beta are both less or equal to omega plus 1 in the Cantor normal order, and you will just make them 0. So this will be an ideal of your matrices rings, and the quotient under this ideal will be a finite matrices group, such that a finite matrices group over this ring, and it will be a profinite ring such that if this coordinate, for instance, is non-zero, in the quotient it will still be non-zero. So the idea is that you can write the group as an inverse limit of profinite rings, and with this, it will also be a profinite ring. And the other result is that given two ordinals, you can define ideals in a smart way too, such that you are kind of cutting the matrices to be smaller. And then the quotient, if one ordinal is greater or equal than the other, you can make this quotient such that you have a surjection from the matrices rings from one to the other. And last but not least, if you have a ring such that you have these properties, so all the finitely matrices groups are all non-isomorphic for n in the natural numbers, then given two ordinals less than omega squared, the groups will never be isomorphic. So here you are just also cutting in some way that you will get a lot of these finite matrices. And by having that they are non-isomorphic for all natural numbers, you can get this result. And some questions that we still want to answer about this, like this last proposition, we still want to know when given a ring and some ordinal, some two ordinals, when can they be, the rings defined by it can be isomorphic or not. So is it true that given P a profinite ring that we can find gamma 1 and gamma 2, two different ordinals, such that the matrices rings will be isomorphic? And a simpler way to ask the question, another question that would be kind of related to it, is given gamma an ordinal and P a profinite ring, in which conditions is it true that we can get the triangular matrices groups isomorphic to a ring? These both questions are related, and they will be quite useful to understand when we want to, for what we desire to do, like we want to make groups elementary groups indexed by these ordinals with these profinite groups as subgroups of it. So if you have something that starts to be isomorphic at some point, we already have a problem here for at least what we wish to do. And another question that is more related to the elementary thing is which totally disconnected locally compact second countable groups can we embed these compact groups as compact and open subgroups? And can we make it in such a way to increase the elementary rank? And like we are looking here at ordinal numbers, but we this kind of construction can also be generalized for other partially ordered sets. So given a class of partially ordered sets and defining rings in a similar way as we are defining here, under which conditions can we give these rings a profinite topology, and when they will also be non-isomorphic? So these are the main questions that we are trying to work at the moment. And yeah, that's what I have to say today. Thank you.
Okay, thanks very much, João. Any questions for the speaker? Maybe a basic one for me. How do you try and prove that for two different ordinals, two of these matrix groups are not isomorphic?
So the main ideas that I'm trying to work with are looking at the quotients. So for example, here I already, this result here would be one of the main ones, right? So you have surjection from things before. So it would be easy with this. How can you get this one, for instance? With this, assuming that the finite matrices, finite triangular matrices will not be isomorphic, you have that omega has a surjection to all the ones before, right? So with this, you have the tri-omega cannot be isomorphic to any of the finite ones before. And what we will do after that, for instance, when you have omega plus 1, let's go back one slide. Omega plus 1 will be just this one matrix. So what do you have here? You have omega, and if you just cut this path, you can just, this will be the things that have this as non-zero, and this can be 0, this is 0, and this as non-zero. This will be an ideal such that the quotient will be just a product of two p's, like p squared. So the idea here would be working with these different quotients that you get to show that it will start being different in some sense. Like here, you have all the omegas, and then you have two independent coordinates after omega. And I don't know if I'm making much sense of it, but.
Yeah, oh, that's a good answer. Thanks. Any other questions? Then in that case, let's thank João once again.